In this next section, we're going to look at which conventions will hold up and be evolutionarily stable. We might think the answer is only those conventions which are best in terms of, say, Kaldor-Hicks efficiency or Pareto efficiency, but this is not going to be the case. We will try to discuss how conventions could be formed, but more importantly, which types of conventions can be maintained and last, i.e., how can we show that a convention is stable, that it will be able to be maintained, that it is something that a bunch of people could follow within a context. As Sugden puts it in the paper, if conventions were the result of deliberate collective choice, we might expect that inefficient conventions would not be chosen. But conventions are not chosen. They evolve. Once a convention has started to evolve, once significantly more people are following it than are following another convention, a self-reinforcing process may be in motion. That stability is what we're going to try to make sense of and what we're going to try and showcase with game theory here. So what is stable in our hawk-dove game here? Is dove-dove stable? Is this a stable outcome that we would have? I mean, after all, this is Pareto superior to our mixed strategy Nash equilibrium play, where each player plays their mixed strategy Nash equilibria, and the expected payoff for each player is 1/3 and 1/3. Right? So this is a Pareto superior outcome to our mixed strategy Nash equilibria play, just everybody plays dove. But is this stable? That's what we're trying to look at here. If we are at this 0.5 payoff of dove-dove, is this stable, right? And the short answer is no. If we're at this 0.5, you could see that player one would like to deviate from this strategy and move up to a payoff of 1, right? And so if the original play is this dove-dove strategy, player one would love to deviate from this. So if player two is still playing dove, right, if we're still here, player one is going to want to move from this outcome of 0.5, and so they will likely kind of cheat the arrangement or the convention of dove-dove, right? So it won't be sustainable. Player one is going to continue to just keep playing hawk if player two plays dove. And likewise, we could do the same kind of logic and say, well, what if player one is playing dove and player two is supposed to be playing dove, right? Is player two going to just stay here? Is this going to be a stable outcome where we end up in this kind of crosshatch here, where both overlap? And the short answer is going to be no, it's not going to be. If player two is in this situation, player two would like to deviate as well and get that payoff of 1 instead of 1/2. So both players are going to have an incentive to deviate from this situation, even though it has a Pareto superior outcome to the mixed strategy Nash equilibria, where the expected payoff is 1/3 and 1/3. So what we should do here is we should recall that we have 3 Nash equilibria to choose from. We have the pure strategy Nash equilibria of dove-hawk, the pure strategy Nash equilibria of hawk-dove, and then also the mixed strategy Nash equilibria. Only Nash equilibria will be capable of being stable. If we don't have a Nash equilibria, a player will deviate from this play and make themselves better off, and thus we won't have a convention or a stable outcome as a result. This is what we just showed with the dove-dove approach of not being stable. We didn't have a Nash equilibria, and so it's just going to fall apart. The mixed strategy Nash equilibria actually could potentially be stable, as could these two pure strategies that we have. So the mixed strategy Nash equilibria has this expected payoff of 1/3 for both players, and the two pure strategy Nash equilibria that we have depends on some kind of focal point or signal, like our A or B from our paper, but once received, it generates these payoffs of 0/1 or 1/0, depending on which focal point has been selected. So which of the 3 Nash equilibria is evolutionarily stable? That's what your paper is going to go through now. So we're going to see, are the pure strategy Nash equilibria evolutionarily stable? Is the mixed strategy Nash equilibria evolutionarily stable? That's what we want to analyze. We're going to use game theory to be able to do this, and we're going to come back to the paper now and see how we work through this problem and try and analyze the situation and see what's evolutionarily stable. All right, so the paper is really going to consider three different strategies for a convention here. So we have three strategies, 1, 2, and 3. One is basically pretty straightforward. If you get a signal A, you play hawk. If you get signal B, you play dove. Right? So in this case, we're trying to coordinate on one of the pure strategy Nash equilibria. Signal 2 is kind of a little tricky here. We're not really going to analyze signal 2 very much. Basically, this is like saying, do the opposite of what you're told, which turns out is a reasonable coordination strategy if we could get everybody to do it. So this is in essence like a situation where we say, hey, everybody drive on the right side of the road. And everybody does the exact opposite and drives on the left side of the road. We actually still do get coordination, but right, this isn't really a realistic thing for the analysis of the development of conventions for us here. So signal or strategy 2 here is pretty much going to be wiped out, and we're not really going to look at this strategy 2. We're really going to analyze strategy 1 and strategy 3. Strategy 3 is basically play a mixed strategy Nash equilibria. So play hawk with a probability of 0.33 repeating and play dove with a probability of 0.66 repeating. All right, and so we're going to look at these two potential strategies, strategy 1 and strategy 3, and see what do we have in terms of stability here. Will any of these strategies lead to stable outcomes or lead to what we could call a convention that would stick, an evolutionarily stable idea here? That's what we're really looking for. So we're going to analyze, as we said, options 1 and options 3 here and show you the math now. So let's start off with strategy 3 here and just think about strategy 3, the mixed strategy Nash equilibria. If everybody's playing the mixed strategy Nash equilibria, then the expected payoff is 1/3, right? Is this stable? Well, let's imagine the situation where everybody is playing the mixed strategy and everybody is getting an expected payoff of 1/3. Let's think about deviating from this strategy. Let's have player 1 be our deviant. If player 2 continues to play the mixed strategy Nash equilibria, and player 1 plays strategy 1 instead. Strategy 1 is that if you get signal A, you play hawk, and if you get signal B, you play dove. So 50% of the time, we are saying we are going to play hawk, and 50% of the time, we are going to play dove. Okay, what is our expected payoff in this situation? Well, we just said player 1 is going to play hawk 50% of the time, right? And so we can look at this payoff here, say, okay, player 1, we're going to play hawk 50% of the time. Player 1, we're going to play dove 50% of the time. So that's the probability that we would be in these cells according to player 1. But then player 2, we also have, and player 2 is playing the mixed strategy Nash equilibria, which has a 1/3 chance of playing hawk and a 2/3 chance of playing dove. And so what we have to do is we have to multiply these probabilities by each other to figure out what is the probability that we are actually in these cells. So we can come through and do the simple math here and say, okay, well, what's the probability that we are in the hawk-hawk cell in this case? Well, we have a 1 out of 6 chance of being here, right? So we have a 1/6 chance being here, and then we have a 2 out of 6 chance of being here, and the same at the dove row here. We have a 1 in 6 and a 2 in 6 chance, right? So that is our probability that we will be in these corresponding cells if player 1 plays strategy 1 and player 2 plays strategy 3, right? So we started in a world of all strategy 3, just mixed strategy Nash equilibria happening. But then we say, what if player 1 deviates? What if player 1 plays strategy 1? So half the time they play hawk, half the time they play dove. We're going to end up with these being the probabilities for the corresponding cells. And so now we want to look at player one's payoffs from this, right? So player one is going to have this payoff where in this first cell, hawk, hawk, we are there 1/6 of the time, and the payoff would be a -1. So we have to multiply that probability by the payoff, and we get an outcome of -1/6. For this next cell here, we are here 2/6 of the time, and a payoff is 1, so our payoff is, again, pretty easy math, 2/6. Right? And then in this third cell, we're here 1/6 of the time, but our corresponding payoff is 0. And so our payoff is going to be 0 here. And then the last cell, we have a payoff of 2/6, and the corresponding payoff is 0.5. And so we can see our payoff is 1/6. We can add all of these together. What happens is we can just simply cancel out the 1/6 and the -1/6. 0 shows us nothing. And so we add all of these together and we have a payoff of 2/6 or 1/3. So what we get if we play strategy 1 against people who are playing strategy 3 is we get this payoff of 1/3. Well, this is true for any strategy against a mixed strategy Nash equilibria. Right? That's the whole point of a mixed strategy Nash equilibria, to leave the opponent indifferent. Any strategy against a mixed strategy Nash equilibria will lead to a result of a payoff of 1/3. But here we've gone through and we've proven that, right? So has the deviant, the person who played strategy 1, player 1 in this case, have they done less well than the conformists who have stuck to strategy 3? Those who keep playing the mixed strategy Nash equilibria? The answer is no. We have not done less well than those who have conformed and stuck with the mixed strategy Nash equilibria. We've done equally as well. We have this payoff of 1/3. So the stability of strategy 3 is starting to unravel a little bit on us here. It doesn't really matter what you do if most people are playing strategy 3, the mixed strategy Nash equilibria, people can deviate from that strategy, right? And so we're trying to see is something stable. So let's look at how this option strategy 3 is going to unravel completely and how other strategies like strategy 1 can become stable, right? And can come about. So imagine you're in a situation where player 1 continues to be a deviant because it's not doing less well by deviating. Given it's not harming her at all against those who continue to be conformists and play the mixed strategy Nash equilibria. But now let's say occasionally she runs into another deviant playing strategy I. So let's say 10% of the time, this player runs into other people who are deviating like she is. What is player 1's expected payoff now, given that there's a 50% chance of receiving an A signal and a 50% chance of receiving a B signal when the two strategy 1 individuals interact? Right? And so we can just basically do some simple math here. 90% of the time, you're still going to be playing against a mixed strategy Nash equilibria individual, a conformist, a strategy 3 individual, right? So 90% of the time, you're going to get a payoff of 1/3. But 10% of the time, right, we're either going to get an A signal or a B signal and play against a strategy 1 person, right? So 10% of the time, we're going to say, 10% of the time, we're going to get an A signal, which is going to say, hey, we're player 1, let's play hawk, and the other person will play dove, right? That's the A signal for us. That's what we want to see. We're going to get a payoff of 1. So half of the time in these scenarios, we're going to get a payoff of 1. Now, this is only happening 10% of the time, but half of the 10% of the time, we're getting a payoff of 1, which is great. The other half the time we get a B signal, and that tells us as player 1 to play dove, and it tells player 2 to go ahead and play hawk. And so we end up with this cell here, the dove hawk cell, and as player 1, we will receive a payoff of 0. All right, so we can look at the simple math of this and say, okay, what is my expected payoff then? 90% of the time, I expect a payoff of 1/3. And then 10% of the time, I'm going to be in a situation where half the time I get a payoff of 1, and half the time I'm going to get a payoff of 0, right? And so the expected calculation, or the expected payoff calculation here, is that 90% of the time we get this payoff of 1/3, and then 10% of the time it gets divided up, where half the time we get this payoff of 1, and half the time we get this payoff of 0, right? So when we do that math, we can calculate this through, and we see that the expected payoff in this situation is 0.35. Now, why does this matter at all, that the expected payoff here is 0.35 for the deviant, if there's a few other deviants also out there, right? And we should take a moment here to note that like this group of deviants may end up kind of deviating together. So if there's some other deviants out there playing strategy 2 or something like that, they could emerge as well, but you might kind of create kind of little subgroups of deviance. So it might be that we kind of leave behind some other people trying to play strategy 2 or other things. But what we're going to see is that strategy 3 is not stable, because playing strategy 1 against strategy 3, even if there's only just a few other people who are playing strategy 1, leads to this payoff of 0.35. And what we can see is that that payoff of 0.35, the deviant payoff, is greater than the mixed strategy Nash equilibria payoff. And in fact, you can kind of do the math here and see that the mixed strategy Nash equilibria payoff is actually reducing if we get some deviance in that situation as well. And so people who are playing strategy 1 are going to get higher payoffs than people playing strategy 3, and thus people playing strategy 3 would like to deviate from this, and hence that strategy is not stable then. It is not stable. And so we're going to see this kind of worked through and discussed in the paper now, where we see that strategy 3 is not stable, and we're having this movement towards the option of strategy 1, or playing kind of the pure strategy Nash equilibria with some kind of signal, with the A or B signal.